Hello everyone, welcome to the Makri Virtual. Hope you are doing good. Today I'm going to continue with chapter number 5, that is optimizing the program performance. Today is the last class for this chapter, and from tomorrow onwards I will start with a new chapter. So today's topic is the next topic, that is after the topic which we have finished in the last class. The main topic is how to remove the bottlenecks so that to improve the program performance. So first of all, let's take a quick recap of the previous class, what we have covered in the last class. In the last class, we have covered about the limiting factors. What are the limiting factors that is available that affects the program performance? First of all, there is a chapter or there is a topic named global register allocation. That is how globally we can allocate the registers in a program so that graph coloring can be done in an easiest way. So it contains three parts, that is global, then approach, then graph coloring. Global means that is beyond the boundary or that can be accessible beyond the boundary, that is a global. Then approach, that is a register allocation as a graph coloring problem, that is your approach. Then we have studied about the graph coloring, that is every node have a different color so that we can approach or we can differentiate between the different edges. Suppose there are three edges in this, and this is a unidirectional, that is there is no direction, this is a undirected graph. So how can we represent that which edge represents which column or which edge represents which nodes? So that can be represented by using the color of the edge. So that is, if D or C combination is represented by the red color, that is a different edge. Here this is a different edge. Here this is a different edge. Although the nodes are same, but the names of the edges or the edges colors are different. Then we have studied about the nodes that are only variables and the edges that are the interference or that are the lines among the variables. Then we have also talked about the live ranges, that is how we can differentiate, how we can use the subsets of the definition and use of the variable so that no other variable uses the same name or no uses of the variable in the minimum subset uses the same value. That is, the variable is unique in every program. Its value depends on the program to program, but the value is the same value. Then live ranges continue. We have talked about this thing, that is diagram also, that is how we can represent the live range. Then we have also talked about the global register allocation, that is how globally register will be allocated or how globally register will be allocated to more than one place. That is how we can reach the or how we can access the variable in the program that is globally declared. So we can use the nodes in the program, we can use a different color of the graph so that it can be used to make the graph or make the nodes represented in the graph. Then we also talked about the advanced branch prediction, that is how we can predict the advanced branch or how we can predict for the advanced branch. That is how we can represent the flow of the program so that it can be represented in a safest way. That is, the first topic we have covered in this is the control flow speculation. That is, what is the control flow speculation? That is the branch speculation or the misspeculation recovery. Then next part is your branch direction prediction, then branch target prediction, high bandwidth or the high frequency. We have discussed all these advanced branch prediction in the last class. Then we also discussed about the branch speculation, that is how to use the branch speculation. What are the parts of the branch speculation? That is leading or trailing. These are the two types, that is leading speculation and the trailing speculation or trailing confirmation. This is a branch speculation that will be discussed with the help of the diagram. This is a diagram. There are three tags, tag 1, tag 2, tag 3. These are represented or shows the different path between the different nodes. Then misspeculation recovery, that is how we can do the recovery if there is a misspeculation, that is speculation is done misappropriately, that is how we can recover the misspeculation. First of all, start the new correct path, eliminate the incorrect path. So first of all, start with the new correct path, that is first of all make the new edge that connects the different computers. Then eliminate the incorrect path, that is we can eliminate the path that is incorrectly used in the program, used in the flow of the program. Next one is your assign branch tags, that is how we can assign the multiple numbers of the tags, multiple numbers of the programs. Then we also discuss about the track instruction groups. This is the program control flow. This is your FA multiplexer, branch predictor, fetch, decode. We have discussed all these things in the last class. Then we also discuss about the next branch prediction, that is static branch prediction. So one is dynamic, one is static branch prediction. These are the heuristics that is used in the static branch prediction. These are the heuristic names and their description. That is loop branch is used to go to the head of the loop, that is at the starting of the loop. There is a return, there is a call, there is a store, there is a guard, there is an opcode pointer. There are two types, or there is a one type of static branch prediction, one is your profile based. This is the performance that is 75 to 80% accuracy. This is your static branch. Now, dynamic branch prediction. What are the advantages and what are the disadvantages of using the dynamic branch prediction? These are the main advantages. That is less branch behavior autonomously. That is, it can behave or it can run the program suddenly. That is at the compile time only. Then it adapts to change branch behavior. It was proposed in launched in 1979 to 1980. It is continually refined since then. This is the diagram that shows the Smith predictor hardware. This is two-level branch prediction. That is how the more than one branch history or how more than one branch can be used for the computer software or for the computer program that increases the performance of the program. Then next topic we have discussed about the memory hierarchy. That is, what is memory hierarchy, what is cache memory, that is your next topic. And the main topic is understanding the memory performance. This is your memory hierarchy. That is, what is a memory? That is the essential component of any computer system and a digital computer, since it is needed for storing the programs and data. As it accumulated all the information that is needed by the CPU at the same time. Therefore, it is more economical to use low-cost storage devices to serve as the backup for storing the information that is not currently used by the CPU. That is, it is very cheaper or it is very economical to use the low-cost storage devices to serve as a backup. So that is the main memory. It serves as a backup. Suppose I forgot my password. I go to the memory, I go to the word that's saved in my memory, they're saved in the computer memory that is used for the memory. So memory hierarchy means we can store the data and we can arrange the different memories in the computer system. This is the how CPU has outweighs dynamic RAM. That is, this is a graph that represents how memory will grown up among the different years, among the successive years. These are the years. These are the different performance levels. This is at 0, 10, 100, 1000, 10,000, 100,000. This is a line that shows the performance of the processor. This is a line that shows the memory. There is a huge gap between the processor and the memory. How do architects address this gap? There is we have studied how to architects address this gap by using the cache memory. So cache memory lies between the CPU and the main memory. Now, what are the types of memory? The memory that is internal is known as the main memory. The memory that is external, that is used for backup, that is known as the auxiliary memory. And one is your cache memory that lies between the CPU and the main memory. That is very fast as compared to the main memory. This says CPU logic is usually faster than the main memory access time, with the result that processing speed is limited primarily by the speed of the main memory. The cache is used for storing the segments of the program currently being executed in the CPU and temporary data frequently needed in the present calculation. That is, cache is more accessible, that is, it is more faster than the main memory, it is usually more faster than the auxiliary memory. So this is the main slide shows the cache memory representation. Then main memory is also divided into two parts. One is RAM, one is ROM. RAM is random access memory, ROM is read-only memory. RAM is again divided into two parts. One is static RAM, one is dynamic RAM. There are a difference. Static RAM is more faster, but it is more expensive as compared to the dynamic RAM. This is the differentiation between the static RAM and dynamic RAM. Then ROM, that is used for permanently residing the memory. The best example is that when we boot the computer, when we start the computer, there are two or more screens that is available when we start the computer. That screens are stored in the ROM, that is your ROM chip. Then main memory, that is the ROM chip or RAM chip. This is the diagram for the RAM chip. These are the multiple selectors, these are the multiple chips available, that is CS1, CS2, RD, read, write, add, that is your address part. Then this is your ROM chip, that is CS1, CS2, 5.2 into 8 ROM, this is your address part, that is your 8-bit bus system. Then we also discuss about the memory address map, that is how we map from the main memory to the cache memory. Then we have discussed about the cache memory. What is cache memory? How it will affect or how it will increase the performance of the program. So whenever computer or the CPU finds the void in the cache memory, that is known as the hit. Otherwise, it is known as the miss. And the hit ratio is hit upon main or divided by hit plus miss. There are three types of mapping available, that is associative mapping, direct mapping or set associative mapping. We have discussed about the cache performance, that is what are the advantages of cache. Then we have also discussed about the average memory access time, that is how we can access the data from the memory. What is the average speed from which we can access the data from the memory, that is known as the average access or average memory access time. So the formula that is used. So that's all for yesterday's session. Now let's start with the today. Today, the next topic is your life in the real world, that is performance improvement techniques. That is, what are the techniques available to improve the performance of the program or to improve the performance of the program that is executing in the computer. Now let's see what are the techniques available. This says we have discussed a number of basic strategies for optimizing, that is for increasing the program performance. So one of the important technique or one of the improvement technique is high level design, that is choose the most appropriate algorithm and data structure for the problem. High level design means the designing part is very high, the algorithm part is very high, the structure part is very high, that is your high level design. So use various algorithms, various data structure that is used for the high level designing so that they may or it may improve the performance of the program, or it may optimize the program performance. So this is one of the alternative or one of the improvement technique. Next technique is your basic coding principles. That is, avoid the import or high level languages like .NET, Java, but use only simple languages, that is basic coding principles that increases or optimize the program performance. This says avoid optimization blockers so that a compiler can generate or execute an efficient code. That is, eliminate the excessive function calls, eliminate the unnecessary memory references. So this is one of the important technique or improvement technique. Then next is your low level optimization. Use unroll loops to reduce the overhead and to enable the further optimization. So this is another technique, improvement technique, that how we can increase by using the low level optimization, by using the unroll loop, find the ways to make the parallelism, that is more than one task are executing at the same time. That increases the improvement, or that improves the performance of the program, so that program will be executing in the computer in a faster way. A final word of advice. So these are the three methods or improvement criteria that are used to optimize to increase program performance. That is high level design, basic coding principle, low level optimization. This is a final word of advice to the reader is to vigilant to avoid introducing errors as you rewrite the program in the interest of efficiency. That is, it is better for the programmer to rewrite the program without any coding error, so that program will increase the performance or improve the performance. This is an example. For example, checking code that uses loop unrolling requires testing for many different loop bounds to make sure that it handles all the possible number of single-step iterations required at the end. This example says uses the simple programming language, uses the simple language so that it increases the performance or it handles the possible outcomes that is used for the single iteration. That is, when we use the loop, that is used for the single iteration. So these are the three techniques that increases the performance of the program. Next topic is your important topic, last topic of this chapter, that is identifying and eliminating the performance bottlenecks. What are the bottlenecks? These are the hindrances or these are the limitations that affect the performance. So this is identify, that is first of all identify the hindrance or limitations, then eliminate the limitations that affect the performance of the program. So the main topic is identifying and improving the performance or eliminating the performance bottleneck. That is, first of all, find the hindrances or the limitations, then eliminate the limitations so that it increases the performance of the program. Up to this point, we have considered optimizing small programs when there is some clear place in the program that limits its performance. Therefore, should we focus on our optimization efforts. But when we working on the large computers, on the large number of coding, then we use the code profiles or code profilers that increases the performance, that collects the performance data, and then uses the optimization technique, that is AMDAHL'S. Now, see what are the bottlenecks and what are the approaches, what are the formulas that is used for increasing the program performance. One is your first topic is your program profiling. That is, it involves running a version of a program in which instrumentation code has been incorporated to determine how much time the different paths or different parts of the program require. That is, how much time it takes or what instrumentation or what are the techniques that is required to determine that how much time it requires for a different programs for different parts of the program. That is a program profiling. Now let's see with the help of PPTs. That is chapter number 5 continued. What are the learning objectives? First of all, predict performance of the parallel program. That is how to predict what is the performance of the parallel program, that is when we are executing more than one program at the same time. How we can predict? First of all, accurate or find out the accurate prediction of the performance of a parallel algorithm that helps to determine whether coding is worthwhile or no. So first of all, find the accurate prediction of the program that is run in parallel. Then understand the barriers to high performance. Then understand what are the hindrances, what are the barriers, or what are the bottlenecks that restrict the high performance or that restrict the performance of the program. This says it allows you to determine how much improvement can be realized by increasing the number of processors used. Then what is the outlining? What is SPEEDUP? Superlinearity issues, SPEEDUP analysis, cost, efficiency, AMDAHL law. This is Gustafson's law, AMDAHL effect. These are the topics that we have discussed in the today's class. Now, first of all, SPEEDUP. SPEEDUP measures increases in running time due to the parallelism. That is, whenever we increase the SPEEDUP or whenever we use the SPEEDUP measure that increases the running time due to the parallelism, the number of P's is given by n. Based on the running times, Sn equals to Ts upon Tp, where Ts is the execution time on a single processor and Tp is the execution time using a parallel processor. So the formula is Ts upon Tp. For theoretical analysis, this Ts and the Tp or divided by Tp are the worst cases or the worst running time for the parallel algorithm or the running time for the fastest known sequential algorithm. So on the basis of running time, we can say how it will execute on a single processor, that is Ts, and Tp is the what is the execution time when using the parallel processor or parallel processors. For theoretical analysis, we use Ts is the worst case or the worst analysis for running the program, and Tp is the worst case for running the parallel program. This is SPEEDUP in smallest, simplest term. This is Quinn notation, that is omega n comma p. Then what is linear SPEEDUP? Usually optimal, that is SPEEDUP is linear if Sn equals to omega n. This is the theorem, this is the proof. This says we shall later see that this proof is not valid for certain types of non-conditional problems. Unfortunately, the best dial-up or the best SPEEDUP possible for most applications is much smaller than n. That is, the optimal performance assumed in last proof is unattainable. So these are the multiple linear SPEEDUP optimal spaces that is used for the optimizing the performance, that is used for increasing the SPEEDUP of the program. Example, recall the blocking can occur in message passing. Then next is your superlinear SPEEDUP, that is how we can use the superlinear method to increase the performance of the program. That is that occurs when Sn is greater than n. This says most of the text besides AKL Quick argue that linear SPEEDUP is the maximum SPEEDUP obtainable. This is the theory that is used for the superlinear SPEEDUP. This is the extra memory that is used in parallel system, so on, so on. This is one of the person that is selling AKL has given a multitude of examples that establishes that superlinear algorithms are required for non-standard problems. That is, there are some limitations in the superlinearity problem or superlinearity method. If a problem occurs, either cannot be solved or cannot be solved in the required time without the use of parallel computation, it seems to failure to say that Ts, that is your time that is used for the parallel system, is equals to infinity. So if the error comes, that then we assign, or the program or the computer assigns Ts equals to infinity. This is the reason why it is assigned to the infinity. Example includes non-standard problem involving. These are the theory that is used for the program. Real life situations such as person who can only keep a driveway open during a severe snowstorm with the help of friends. Some problems are natural to solve using parallelism, and sequential solutions are inefficient. The last chapter of AKL textbooks and several journal papers of AKL were written to establish that superlinearity can occur. So this is the last topic that when we studied AMDAHL'S law. This says it may still a long time before the possibility of superlinearity occurring is fully acceptable. For more details on superlinearity, parallel computer model, this is the theorem that is used, or this is the chapter that is used in the classes. So this is the analysis, that is, this is the representation. We use the omega sign, pi sign, n comma p equals to Ts divided by Tp. This is the same. Inherent sequential computations are omega n, that is omega n, that is pi n, this is omega n, this is kn. These are the multiple formulas that increases the speed of analysis. This is the execution time for the parallel portion, or when we execute at in a pipelining, that is in parallelism. This shows non-trivial parallel algorithms that is used for the computation components as a describing function of the number of processors used. These are the number of processors used, and this is the time. That is, one processor uses less time, another processor, next processor. These are the processors, and these are the time limits for the parallel processing. That is, these processors are executing at the same time. This is the time for communication. This is the time for parallel process. This is the time for communication. This is the time. This takes more time. This takes less time. This takes equal time. This processor takes, these four processors takes equal time, and all these processors also takes equal time. Shows a non-trivial parallel algorithm communication component as an increasing function of the number of processors. This is the execution time of parallel portion, that is omega n divided by 4 p plus k n into k comma p. These are the multiple problems that is denoted by the processor and the time. So this is the combination. This is denoted by blue, that is parallel system. These are the communication problem. This is the combination of the parallel as well as the communication problem. This is blue, this is red. Blue, red. This shows various representation, how processor will execute in the program. Now, let's see again. One processor comes, another processor comes, another come. That increases or improves the speed of the, or reduces the speed of the CPU. I'm repeating again like this one. One processor comes, another, next, like this one. Elbowing out. Now, what are the metric components that is used to increase the performance of the programs? The performance metrics introduced in this chapter apply to both the parallel algorithms as well as the parallel programs. Normally, we will use the word algorithm. So, one and the same thing. Either I can say algorithm or either I can say program. The term parallel running time and the parallel execution time have the same meaning. So, if I use parallel running time, if I use parallel execution time, these are the one of the same thing, that is parallelly executing the program, parallelly running the program. One and the same thing that is used in the CPU, that is used in the computers. The complexity of the execution of a parallel program depends on the algorithm is implemented. Suppose I am using a high-level algorithm, so that the complexity of the integrity or the complexity of the execution type of a parallel program depends on the algorithm to the algorithm. Next, what is the cost required for running the parallel program? This is the cost required, that is cost for a parallel algorithm or parallel program. This is our program. Cost equals to parallel running time into number of processors. That is, what are the number of running times or what are the number of processors parallel running time as well as multiplied by the number of processors. Since cost is a much overused word, the term algorithm cost is sometimes used for the clarity. So whenever we use cost, we can also say the algorithm cost, that is equals to parallel running time into number of processors. Next point says the cost of a parallel algorithm should be compared to the running time of a sequential algorithm. Then what are the uses or what are the costs available that removes the advantage of parallelism by changing or charging for each additional processor. That is, whenever we say cost is this one and one processor is increases, that is one more program is running, then it increases or it increases for the cost for the additional processor. Then what is cost optimal? A parallel algorithm for a problem is said to be cost optimal whenever or if its cost is proportional to the running time of an optimal sequential algorithm for the same problem. Suppose I targeted one program one program as a optimal program. Then I calculate the cost for calculating the cost for the execution of that program, that is optimal program. That is suppose it takes 10 nanoseconds. Now I am executing another program that takes 12 nanoseconds. If I compare two programs, that is one is my optimal program, that is one is my average program, one is my new program. So when we compare, our new program takes more nanoseconds. So that is, it requires more nanoseconds. So my program is not trustworthy. We cannot trust on the program. So that is your cost optimal. That whenever we compare among the new program or the currently program with the optimal program, that is set as the average program. That is known as the cost optimal. This is the parallel cost, how we calculate, where FT is the running time of an optimal sequential algorithm. By proportional, we means that cost is equals to TP multiplied by N equals to K into TS, where K is a constant and N is the number of processors. This is the same, but I'll give you example. If it is fastest known sequential algorithm is sometimes used instead. These are the bounds on the efficiency, that is decode. For algorithm for traditional problems, superlinearity is not possible and speedup is greater than equals to processor. Since speedup is greater than equals to 0 and processor is 1, then it is a formula or it is a algorithm, it is a equation that is used in the efficiency. Then next point says algorithm for non-traditional problems also satisfy 0 is greater than equals to omega n comma p. However, for superlinear algorithm, it follows that this is greater than 1. Since speedup is greater than p. So this says what are the effects on the efficiency. Now, let's say with the help of book, that is what we have covered or what is discussed in the book. One is your program profiling, that is how to run different versions of the program. what are the CPU time that is taken for running the program. For example, Unix system provides a profiling program that is GPPRO. This program generates two forms of information. First of all, it determines how much CPU time was spent for each of the functions in the program. Secondly, it computes a count of how many times each function gets called and categorized by which function performs code. That is, program profiling means first of all identifying how much time the CPU requires and how much time the CPU takes for executing the program. Secondly, it computes or it compares a count of how many times each function gets called in the program. That is your program profiling that affects the program efficiency or that affects the performance of the program. If there are large number of loops available, if there are large number of bottlenecks available, that becomes a hindrance of the program. This is the example that is discussed with the help of Unix. Today my system is so slow due to the network problem. There is low bandwidth. Then how using a profiler to guide the optimization. That is how we can use the profiler to make the optimization by using the concept of the igram, Shakespeare, program performance that increases the performance of the program. This says our program consists of following parts. We created multiple versions starting with the simple algorithm for different parts and thus replaced with the sophisticated ones. That is, first of all, the target or the achievement, the rule is that each word is read from the file and converted into lowercase. That is, the program content must be in the lowercase. Our initial versions use the function lower1, which we know to have quadratic runtime due to the repeated call to the strlen. So the first point says use the small letters in the lowercase word, use the small letters in the coding part of the program. A hash function is used to create the number between zeros and ones. Each hash bucket is organized as a linked list. That is, this is the form how it will initialize or how it will use as a linked list, that is one after the another. This is your sorting, this is your list, this is your lower part, this is your hash or hash table. This is a diagram that shows the different versions of the frequency. Then strlen, what is the use of strlen? That computes the string length. Suppose I have two strings, one is your hello and one is your key. Then if I want to compare the two strings, that can be done by using the strlen function that is used in the programming language to compare the two strings. What is string? That is a collection of characters. Then next is your hash that computes the hash function. Then rest that sums the other functions or that sum of the or that adds the other function that is used in the programming languages. This is a theory or this is the example that is discussed how it will increase the performance. That how it will use, that is strlen, that is strp that is used for increasing the length, for increasing the performance of the program. That if a program takes 9 minutes to execute, then it will take strlen function to execute the program to calculate the length of the string. Now, next is your AMDAHL'S law. Now, let's see. This is your AMDAHL'S law. that is let f be the fraction of a operation in a computation that must be performed sequentially, where 0 is less than equals to f. That is 0 is less than equals to f, that is less than equals to 1. That is, it lies between, the function lies between the 0 and the 1. It also equals to the 0 and also equals to the 1. The maximum speed is achievable by a parallel computer with n processors, that is n number of processors. So this is the syntax, that is omega sp is less than 1 is less than 1 f. The word law is often used by computer scientists, that is used by the scientist when it is an observed phenomena. So the law is used whenever there is an observed phenomena, whenever there is a syntax, there is a rules regulation. So it uses the terms law for operating or used as the method or the rules regulation that is used by the computer scientist. For example, Moore's law and not a theorem that has been proven in the strict sense. However, AMDAHL'S law can be proved for the traditional problems. This is the proof for the traditional problems. That is, it says if the fraction of the computation that cannot be divided into concurrent tasks is f and no overhead incurs when the computation is divided into concurrent parts, the time to perform the computation with n processor is given by. So this is a formula that is given by the processor, or that is given by the AMDAHL'S law. That is TP, that is time taken to execute the parallel program, is greater than equals to FTS, that is used for single processor, plus 1 minus f into TS divided by n. This is the diagram that shows representation of the AMDAHL'S law. This is the preceding expression for TP, for TS. Now this is the proof that is used for the TS, that is Sn, that is the sum of the number is equals to TS divided by TP, that is always less than equals to the n part. Assumption only valid for the traditional problem. Now question, where is this assumption used? The pictorial representation of the argument is taken from chapter 1 of the Wilson and Array. Sometimes AMDAHL'S law or the AMDAHL'S law is simply represented by Sn is less than 1 divided by f. So these are the formulas that is used in the AMDAHL'S law for increasing the performance of the program. Now, what are the consequences of AMDAHL'S limitations to parallelism? So first of all, let's take 5 to 10 minutes break and then come back starting with the next topic, that is what are the consequences or what are the limitations of the AMDAHL'S law to the parallelism. So first of all, let's take 5 to 10 minutes break, then come back starting with this topic on. Now let's start with the next topic, that is consequences of the AMDAHL'S or the limitations to the parallelism. That is your main topic or next topic. This says, for a long time, AMDAHL'S law was viewed as a fatal flaw to the usefulness of parallelism. That is, AMDAHL'S law is very useful whenever we use the parallel program, that is more than one program are executing at the same time. AMDAHL'S law is valid for traditional problems. Traditional problems means that is very prior problems and has several useful interpretations that is used for interpreting the commands of the or limitations of the parallelism. Some textbooks shows that AMDAHL'S law can be used to increase the efficiency or the efficiency of the parallel algorithms. AMDAHL'S law shows that efforts required to further reduce the fraction of the code. That is, it shows that there are more effort that is also required, or there are more capabilities that is required to further reduce the fraction of the code that is sequential may pay off in a large performance gains. Hardware that achieves even a small decrease in the percentage of things executed sequentially may be considerably more efficient. That is, the hardware that achieves even a small decrease in the percentage of the things that is executed sequentially or that is executed in a sequence manner may be considered as the more efficient way to increase the performance or to increase the parallelism, that is, more than one program are executing at the same time. Now, what are the limitations? Last slide shows what are the advantages for using the AMDAHL'S law with respect to the parallelism. That is, more than one programs are executing at the same time. Next is your limitations of AMDAHL'S law. That is, what are the limitations of AMDAHL'S law? This is a key flaw in past arguments that AMDAHL'S law is a fatal limit to the future of the parallelism is Gustafson's law, that is the proportion of the computations that are sequentially normally decreases as the problem size increases. That is, whenever the size of the problem increases, the potential of the proportion of the computation, that is calculation paths, are decreasing very. Note that Gustafson's law is observed phenomena and not a theorem. That is, a observed phenomena, that is live phenomena. It's not a theorem that is used, that we can use the programs, the function. No, that is a observed phenomena. Other limitations in applying the AMDAHL'S law are its proof focuses on the steps in a particular algorithm and does not consider that other programs with more parallelism may exist. That is, AMDAHL'S law applies to only the standard problems where superlinearity cannot occur. That is, whenever we apply the AMDAHL'S law theorem, that applies to only the standard problem that does not increases or decreases, the superlinearity cannot occur. Now, what are the examples? This is most important. Example number 1 says 95% of a program execution time occurs inside a loop that can be executed in a parallel. What is the maximum speedup that we expect from a parallel version of the program executing on the 8 CPU? This is the formula. That is, we are using the 95% of the program. 95% means 0.005. That is, only 5% is left. That is, omega is less than 0.005. This is a pipe that is used. Bracket open, 1 comma 0.005, that is divided by the 8. Then that is equals to approximately 5.9. Why we are using 8? Because there are 8 CPU that is executing. Why we are using 95%? Because this is the internal part that is executed inside a loop. But whenever we execute it outside the loop, that is beyond the 95%, that is a less than, or that is a leftover 5%, that is equals to 0.005. Next, 5% of the parallel program execution time is spent with inherently sequential code. That is, in a sequence code, we can use the 5% of the parallel programs. The maximum speed of achievability by this program, regardless of how many P's are used, is this one. This is the how many P's method, means how many cycles, how many clock pulses, how many CPU execution time is required. That is divided by only P. This is POP quiz. This is a quiz. An oceanographer or oceanographer gives a serial program. This is a quiz. Answer is available. A person or oceanographer gives a serial program and asks you how much faster it might run on the 8 processors. So it gives a scenario that a serial program is running and it will execute on the 8 processor. You can only find out one function amenable to a parallel solution. Benchmarking on a single processor relieves 80% of the execution time. That left time is 20%. So we take 0.2. That is where 20%. What is the best time a parallel version is likely to achieve on the 8 processor? This is mentioned 8. That's why it is divided by the 8. Same process. This is 0.05. This is 1. This is 1 divided by this is 1 divided by 0.2, that is your 20%, addition to the increment to the or add the 1 minus 0.2, that is your less than 20%, that is your 80%, then divided by the 8. Then whole divided by the 1, that is this is your formula. So first of all take 20%, then 80% divided by the 8. Then there is a bracket, that is approximately, this sign is used for the approximately equals to 3.3. This is other limitations of the AMDAHL law. That is, what are the limitations of the AMDAHL law? Recall, AMDAHL'S law ignores the communication code in the MIMD system. That is, it ignores the communication code. It only shows the code that is required for executing the program, But it means AMDAHL'S law ignores the communication code that is required for executing the program. That is the cost required for communication, for transferring the data, receiving the data from one part to the another part. Next is that on communication intensive application, even the K and P terms does not capture the additional communication slowdown due to the network congestion. That is, if there is a network congestion, the communication is slowed down, or the additional communication will require for the network congestion. This says, as a result, AMDAHL'S law usually overestimates the speed of achievability or achievable. That is, it overcomes or it will overestimate the speed of achievability. Now, what are the effects? These are the effects of the AMDAHL'S law. That is, typically communication time, that is K and P, has lower complexity than the phi n upon P or divided by P. That is the time for the parallel port. As n increases, if the n increases, that dominates K and P. As n increases, sequential portion of the algorithm decreases or speed of the or increases the speed of the reliability. Then AMDAHL'S law, speed up is usually an increasing function of the problem size. Now, this is shown by using the graph. This is the graph, this is the speed up problem, this is speed up, these are the processor, n equals to 100. This is n equals to 1000, 10,000. This is the illustration of the AMDAHL'S law, that is how it will increase the speed of the processors. Then next is your review of the AMDAHL'S law. That is, what are the reviews of the AMDAHL'S law? First of all, it treats the problem size as a constant. That is, it treats every problem or every program as a constant, as a similar value. It does not differentiate among the different values. It shows that how execution time decreases when the number of processors increases. That is what we have covered in the AMDAHL'S law. This is shown in that program. That is how one program will be executing with another program. That is how different programs will be executed. So first of all, first point says it treats every problem, that it treats the program or the program as a constant, not the variable. It shows that how execution time decreases when the number of processors increases. The limitation established by the AMDAHL'S law are both important and the real. Currently, it is generally acceptable by the parallel computing professional that AMDAHL'S law is not a serious limit the benefit and future of the parallel computing. Then what are the metric used in the AMDAHL'S law, or what are the ISO efficiency metric that is used, terminology that is used? One is your parallel system, that is more than one program or parallel programs are executing on a parallel computer. Then next is your scalability of a parallel system, that is a measure or metrics that are used to increase the performance as the number of processors increases. Next metric or next terminology is that there is a scalable system, that is we can scale or we can measure the size of the system by using the AMDAHL'S law. That is, a scalable system maintains efficiency as processors are added. Then ISO efficiency, a way to measure the scalability. These are the four metrics that is used in the AMDAHL'S law for calculating the various operations when we use the multiple processor, when we use the parallel system, when we use the multiple systems. Then what are the notations that is used in the AMDAHL'S law? This is your n, that is your data size, that is your variable. Then p, that is your number of processor. Processor means what are the number of CPUs. Then PNP, that is your execution time using the P processor. P processor means a number of processors. The number of processors is P, that is your P processor. Then this is a phi, that is this is the omega, or the phi that is used for the speed up. This shows the speed up and T shows the execution time. In the same way, this symbol that is omega, or that is pi, or that is selection operation is used for sequential computations. Then phi is used for the parallel computation. So this is used for sequential, this is used for parallel computation. Then K and P, that is your communication operations. That what are the operations, or what are the communication operations that is used for the K and P. Then this is omega is used for the efficiency, for showing the efficiency. These are the multiple isolation or multiple notation that is used in the AMDAHL'S law. Note that at least in some printings there appears to be a misprint on the page 117, the quick textbook with this one. This is not used. Now, ISO efficiency concepts. T0 and P is the total time spent by the processes doing work not done by the sequential algorithm. So T0 denotes the total time that is used or that is spent by the processes, that is multiple processing, doing work not done by the sequential algorithm. Then whatever the task that is not done by the sequential algorithm is used or is done or is calculated by the total time that is denoted by the T and P. Then this is the formula that is used, that is T0 and P equals to P minus 1. This is the select operation and plus Pk and P. We want the algorithm to maintain a constant level of efficiency as the data size n increases. Hence, sigma NP is required to be a constant. Recall that T and 1 represent the sequential execution time. This is the in iso-efficiency relationship. That is what is the relationship, how parallel system will work. This says, suppose a parallel system exhibits efficiency that is omega NP, that is defined or that is denoted by C equals to omega NP divided by 1 minus sigma NP. This is not omega, this is sigma, and this is also sigma NP. How we calculate the T0? That is calculated by P minus 1 selection operation N plus Pk NP. These are the relationship derivations that is used. These are the main steps. This is how we can derive. This is the formula derivation that you have to study. Then iso-efficiency relation usage. That is, what is the use of the iso-efficiency? That what is the use of the efficient data that is used for the program execution? The first point says the iso-efficiency relation is used to determine the range of processor. That is, what is the range of processor? What are the number of processor that is used for which a given level of efficiency can be maintained? The way to maintain a given efficiency is to increase the problem size when the number of processors increases. Next point says the maximum problem size that we can solve is limited by the amount of memory available. That is, the maximum problem size is the limited or useful or used whenever there is an amount of memory available. If there is no memory available, we cannot access or we cannot describe the problem. That is, no process will execute the process. No process will execute the problem. Next point says the memory size is a constant multiple of the number of processors for the parallel system. Next, scalability function that is used for representing the scalability, availability of variables. That is, suppose the isosufficiency or the isosufficiency relationship reduces to the n is greater than equals to fp. Let mn denotes memory required for the problem of size n. MFP divided by P shows how memory usage per processor must increases to maintain the same efficiency. This is the formula. This is a scalability function, that is MFP divided by P, that is equals to scale P equals to MFP divided by P. Then what is the meaning of scalability function? That is used to maintain the efficiency. When increasing P, we must increase N. This is a scalability function, shows how memory usage per processor must grow to maintain the efficiency. These are the theory part, or these are the meaning of the scalability function. Yeah, this is the important. This is the diagram or the graph that shows how the number of processors and what are the memory requirement that is used for the scalability function. This is the memory size. This is the CP-LOGP. This is CP. This is C-LOGP. This is C. This is can maintain efficiency, and this is cannot maintain the efficiency. Means beyond the memory size it cannot maintain the efficiency, and below the memory size it can maintain the efficiency. This is the example number 1, that is your reduction part. This is sequential algorithm complexity, that is Tn1 omega n, that is parallel algorithm. This is computational complexity, this is communication complexity. This is parallel overhead. Then reduction continued, that is your main system log, or this is your main formula that is used for the scalability function. This is your next example. This is finite difference. This is the example that you have to study. Now, what are the summaries? Performance terms, that is running time, cost, efficiency, speed up. Then model of speed up, that is how we can use the speed up, that is serial component, parallel component, communication component. So this is the performance terms and model of speed up. Then what are the factors that prevent the linear speed up? Serial operations, communication operations, processor or process startup, and imbalanced workload, architecture limitations. This is what we have covered in the today's class. Now let's see with the help of book, that is what we have covered with the help of slides. This is the AMDAHL'S law that we have studied. This is the formula that is used, as I told you, that is alpha 1 minus alpha plus alpha divided by k. This is your T, this is your T out, this is your T new. So next is your summary, that is the wind up of the chapter that we have covered in this chapter. That this says almost more presentation on code optimization describes how compilers generate, or how compiler can generate efficient code that must be, or that much can be done by an application programmer to assist the compiler in the task. That is how compilers are used, or how compilation method is used to increase the code optimization, to increase the optimization or readability of the. This is what we have covered in this chapter, that is optimizing program performance. This is the graphic notes. This is the homework problems that you have to study. So that's all for this chapter, that is optimizing the program performance. In tomorrow's class, I will start with the new topic, that is memory hierarchy. This is your next chapter, and this is your new chapter that is not related to the previous chapter. This is the new concept, most easiest chapter. Most of the topics we have covered like RAM, ROM, cache memory. This is the whole chapter. I will start this chapter from tomorrow's class. Now, let's take a quick review what we have covered in the today's class. We have discussed about the learning objective, that is what are the uses of parallel programs, how to understand or what is the meaning of barriers to the higher performance. Outline, speed up, superlinearity issues, speed up analysis, cost, efficiency, AMDAHL'S law, Gaussian law, or AMDAHL'S effect. Then we have discussed about the speed up, that is how speed up can increase the program performance or how speed up can increase the parallelism of the program. This is the notation. We have discussed about the theorem that is used for the speed up. We have discussed all these theories, that what is the proof, what is the optimal performance, that is PE, that is your proof. Then this is the formula that is used for superlinear speed up. Then what is the superlinearity? This is superlinearity. This is speed up analysis. This is the speed up definition or speed up analysis of the definition that is used. This is the execution time for the parallel portion, that is how we can use the parallel portion or how we can execute the parallel system. This is the pictorial representation, diagrammatical representation. This is used for parallel proportion. This is used for communication, and this is the combination of the parallel and the communication. This is how different processor will execute in a different slots of time, in a different speed up. Then what we have studied about the metric components or metric commands. Then we have discussed about the cost, that what is the cost for the cost of a program or algorithm cost. This is the formula, that is parallel running time into number of processors. Then cost optimal, we have studied about the cost optimal, that is comparing with the average cost. Then efficiency, bound on the efficiency, what are the limitations on the efficiency. Then we have discussed about the one of the law that is most important law, that is AMDAHL'S law. This is the formula that is used for the AMDAHL'S law. This is the proof of the AMDAHL'S law. These are the consequences of the AMDAHL'S law with respect to the parallelism. What are the limitations? This is the limitation. We will discuss about the examples. This is the quiz that shows how we can calculate the with the help of AMDAHL'S law. This is the AMDAHL'S law. What are the limiting factors? This is the effect of the AMDAHL'S law we have discussed. This is the diagram we have discussed about the effect of the AMDAHL'S law, that is 1000, 100, 10,000. Then we have discussed about the review of the AMDAHL'S law, that is how we can use the AMDAHL'S law. What are the ISO efficiency metric that is used, or what are the metric problem, or what are the measurement that is used, that is parallel system, scalability, scalable system, ISO efficiency. This is the NP different notations that is used in the ISO efficiency relationship. These are the multiple concepts that is used. One is your T0 NP, that is the formula, that is P minus 1 selection operation N plus PK NP. This is the relationship, ISO efficiency relationship. These are the main steps. This is a scalability function we have discussed. This is the meaning of the scalability function. This is the diagrammatical representation of the scalability function. This is the example. This is the summary we have discussed. So that's all for today's session. Thank you so much everyone. Now, if you have any questions, then please text the questions and I will answer it. And tomorrow's class, I will start with the new topic, that is memory hierarchy. That is the new concept, new topic. So that is not related to this topic or the previous chapter. That is the new full-fledged and the easiest topic. So that's all for today's session. Now, if you have any doubts, then please take the doubts. Thank you.